Hi everyone. Today we're going to continue off where we left off. Specifically, we're going to be looking into setting up core DNS or DNS services in a local storage provisioner. Um, in our prior video, we went over the creating or should I say, deploying the worker node components so that we could schedule pods and try to exec into them. We did hit an issue with RBAC, role-based access control, but we fixed it in a post video, which was actually the prior video. So with that, let's get started. So in this chapter, we're going to cover the core DNS, which provides cluster internal DNS, so pods can reach services by example, and then my service.default that serves cluster.local instead of by cluster IP. And then a storage provider, which handles persistent volume claim requests, so stable workloads like databases, caches can dynamically allocate volumes. We will be using Helm in this chapter. It's not going to be difficult, but yeah. Now, what this documentation I have is based off of a prior author's documentation, which I use Claude AI to kind of summarize and remove or tailor to my use case, which in this case is a single node virtual machine K8 system. In their documentation, they use NFS and META-LB. That doesn't apply here. So that's why there's a section on what was removed from the original guide. Now, prerequisites, we do need to be able to SSH into the virtual machine, which we've done already on the right. And all the control plane and worker components should be running. You should be able to do a get nodes and see that the node is in ready status, which we did um, in prior videos, but we'll do that again. So we do have the status script here, which we had been building over time as we were deploying the components. So from etcd, kubeAPI server, the controller manager, the scheduler, the containerd service, kubelet, and the kubeproxy. So while this isn't 100% indicative that the services are working as expected, but it can give you a certain level of expectation that things are somewhat working. Now we will do as the documentation says, and let's just do a get nodes. And as you can see, we do have our node up in ready state. So with that, let's get started. We're going to install Helm. And in this case, we're installing Helm 3. I know there's a Helm 4, but we're just going to stick with what's kind of known and good working. I've already kind of tested this out, this documentation, so that's why you'll see that Helm is already installed through my system. Now let's just do a Helm version just to follow along with the documentation. And as you can see, we do have version 320.2, and it is in the path because I was able to just type in the binary name. Now, with that, let's go ahead and first add the core DNS Helm chart repository to our local Helm. It's been added, and then the next step that we'll do is we'll do an install. I did actually create a kind of a script for this in my downloads folder like I've been doing before. So it is here. So basically, like I showed earlier, you just add the Helm chart to your local Helm, and then you do an install. We could run that. In fact, let's do that. Yep. So now the Helm chart has been installed to the K8 system, and a few things to note as part of this deployment is to really make sure that core DNS services pods are up and running and that it's completely functional before you attempt to try to use any of the DNS services. So let's go ahead and look at the pods for the core DNS, and you'll see that it is running in running state now. It's been up for 39 seconds. Now that the pod is running, we want to confirm that there is a CoreDNS service. There is. Um, and as you can see, it maps, right, with expected output with what we see here. So the next step that I would like to do is to test DNS resolution. And to test DNS resolution, what we're going to do is we're going to essentially run a test pod using that's based off of curl. And then inside, we're going to essentially within that pod, when we run it, we're going to run a curl command against the Kubernetes um, service, and that should give us a response code. That response code, if we actually did get a response code, that means that DNS resolution is working, and we're actually, DNS is resolving to the internal backend IP address of the service, which then submits the request to the service, and that service responds back. So in this case, we should expect to see a 403 because we're not authenticated. So let's go ahead and attempt this command. And as you can see, we did get a 403 response from this curl command. Now, like I mentioned earlier, a 403 response confirms DNS is working. The short name Kubernetes.default is expanded to Kubernetes default.service.cluster.local by the resolver, which CoreDNS resolves to 96.0.1, the API server's cluster IP. The API server returns 403 because the request is authenticated, not because DNS failed, right? That's what I mentioned earlier. Had we passed in the necessary authentication, headers and whatnot, it would have worked. So that's good. Now, the request we made earlier was what Kubernetes.default. And so another thing we could test is to use a fully qualified domain name. So in this case, Kubernetes.default.service or svc.cluster.local. So let's go ahead and attempt that same test. And as you can see, the request did go through, right? Because we got a 403 response back from the server, as it says here. Now, in case you do hit some issues, you should probably go ahead and go through the troubleshooting steps. So, for example, check the logs of the CoreDNS pods. We can do that real quick. So let's do just a git pods minus a. We have a pod in the cube namespace, right? And that's this one right here. So what we're trying to do is inspect the logs for the CoreDNS service in this case. Now, because of the way that the CoreDNS service is configured, the logging is only going to show error and info. So there is another step down here where you can modify the config map for the CoreDNS service, in this case the Helm chart. And what you do is down here where you see the core file section, you can add in the log and log debug. So this should allow us to see more info in the logs of the pod, and I'll show you what I mean by that here in a minute. So let's do a git pods again. I just want to see if it restarts the pod. Let's see, J6BZZ. Yeah, it's still the same pod. That's fine. What we're going to do now is we're going to do another curl. Okay. And we're going to do another logs command. When we do that, you'll see now that we have more information in the logs. I have noticed in my prior test that if I didn't enable logging within the config map, like I did earlier, that it wouldn't show these requests. So, or at least these log entries. So that, in my experience, that's what I had to do. Maybe I did something incorrectly, but um, unfortunately, that's what I had to do in my case to see a little bit more in the logs. So now that the um, CoreDNS is working as we expected, right? Uh, the thing we want to do is actually go back and edit the config map real quick. Let's get rid of this log and debug because it really does bloat up the logs and we don't want that. One thing we can check is the value of the etc resolve call. And let's do that real quick. So it has essentially kept the etc resolve call for this pod, and you'll see the configuration that it has. So the name server is the 10.96.0.10, right? And then you'll see that the search or lookup is enabled for default.service.cluster.local, service cluster.local, and cluster.local. If the name service is not 10.96.0.10, then, or the search domains are missing, the issue is in the kubelet DNS configuration rather than the core DNS. So we would have to look at the kubelet configuration, and we can check that real quick. I think that's in varlib kubelet, and then it might be the kubelet config. So cluster DNS, and then it's using this resolve conf. That's the kind of back end, I guess, of kubelet itself. It says here if the name server is not set. Yep, that's actually fine. This command though looks a little suspect to me, but we were able to confirm that the DNS is set correctly. All right, let's keep moving along. And next thing that I would like to do is install or have the ability to have what's called a local path version. And so the reason you want to do this is if you plan on running like any stateful workloads such as that require PVCs or persistent volume claims, you need storage provisioning. So Rancher, the company, provides an open source provisioner called Local Path Provisioner, which allows you to it deploys a set of components that allows you to dynamically create physical volumes. So all you would have to do is obviously we'll go through the steps, but you deploy the local path provisioner, and then all you would have to do is create the persistent volume claim and your pod to use that persistent volume claim. Internally, the local path provisioner will take care of creating the provisioner the persistent volume dynamically for you. We'll see that here in a minute, and you won't have to kind of do that yourself. So then you would configure your stateful application to leverage that PVC mounted in your pod, which we'll see here in a minute. All right, so let's go ahead and do that. So we're gonna run this kubectl apply command, which will deploy the latest local path provisioner, and it will do a few things, right? So we'll create the local path storage namespace, then it will create a service account, and then it will create the rule and cluster role, plus the corresponding cluster role binding and cluster role binding. It will create a deployment, and it would also create the storage class plus the config map. So two things we're going to do after we've deployed this. First thing we want to do is actually verification. Right? Let's do get pods. Make sure the pod's running. Right. So the provisioner, local path provisioner is running. Okay. And then we want to patch the default storage class. So before we patch it, let's just do kubectl get storage class. And you'll see here that we do have a storage class, but there's no default one. So this patch command will allow us to set the local path as the default one. So let's go ahead and do another get storage class, and you'll see now that it is set to the default storage path storage class, and that's what we saw here. Now we're going to test this local storage path provisioner. So we'll create a persistent volume claim of 128 MI, right? Read once, read write once, and we're going to create a pod of, using BusyBox, where it's going to create a volume using that PVC that we've created, that's PVC, and it's going to the persistent volume claim, right? And then it's going to mount it into the pod at /data. The pod itself, what it's going to do is it's going to just create a simple echo statement into a file called test.txt, and then sleep for 3600 seconds. Now let's go ahead and run this. As this went ahead and created, like I said, the PVC and the pod. So now let's do a get pod. We should have the one that we just created, right? The test, the pods right here, the test PVC pod, right? And then the PVC that we just created, right? And it's bound. Okay, it's important here. Now the reason why it's bound is because the local path provisioner went ahead and dynamically created and allocated the storage on disk for your PVC. Now here, this is the PVC that gets created, and before we go inspecting the PVC, sorry, in this case the PV, what I would like to do is inspect what the test pod wrote to disk. So we're gonna exec into the test pod that we stood up earlier, and then we're going to cat the value that we echoed into the test.txt file, right? So it's just storage test, right? If we go back, right, that was one of the commands that we essentially ran as part of starting up the pod, right? The next thing we want to do is we wanna from outside of the pod, right? Because this is a local based kind of or local host based storage provisioning. One thing you could do is inspect the persistent volume. So this persistent volume that was dynamically allocated for us, we can inspect it, and this will tell us important information about this uh, persistent volume that gets created, right? Specifically, such as like the path on disk where the persistent volume is located. So you can actually cat this file, though it's actually a directory. Um, so the directory maps to the PV name, and then in this case, so the PV name, the namespace, and then the pod, and within that directory, there's the test.txt, right? For example, if I go there and I look, right, I can see the test.txt file that got created as part of the original test pod that we started and we exec into, and then we did this. In theory, if I also cat this test file, I should see storage test, right? That's that's so it was created by the pod. It's saved there. So this would allow my pod to die on me, right? Essentially, if I went ahead and deleted the pod and restarted it, in this case, it would get overridden based off um, um, here. In case if I were to attempt to redeploy it, it would overwrite what's in the test file, right? But if I had, say, a replica set or a deployment, which would automatically restart the pod, or actually neither of those two cases. If I had a stateful set, in that case, it would remount the um, the PVC at that path, and then you would still see it within the pod, or in this case, the container. So we were able to look at the contents of the file, both from within the pod and externally from the pod, from the host side. And now what I would like to do is I would like to do some kind of cleanup. So before deleting, capture the PV directory path so you can confirm it is removed afterwards. So we know what the path is because we're in it, but I'm going to just go up one directory. You can see that the path still exists, right? What we're going to do is we're going to delete this pod, and then we're going to delete the PVC. So and one thing I kind of want to check though is there should be an option. I'm not sure if it's on the PV or PVC around the retain logic. So let's do a get PVC and let's inspect it real quick and see if it has anything around retain. Let's see, access mode, resource requests. So the BBC, I don't see anything in here. And it has a finalizer, but I don't see anything in here about retain. Let's look at the PV, the persistent volume, see if there's anything around, um, around retaining. Okay, so here's the reclaim policy that I was referring to earlier. So it's persistent volume reclaim policy is set to delete. And if you wanted to understand what that means is if you do a kubectl explain and then the kind that you want to explain, which is persistent volume, so in this case persistent volume, it's under spec dot persistent volume reclaim policy. And so there's three different enums. So delete, recycle, retain. In this case, we're doing a delete. So persistent volume reclaim defines what happens to persistent volume when released from its claim. Value options are retain, default for manually created persistent volumes, delete, default for dynamically provisioned persistent volumes, and recycle. Recycle is deprecated, so I'm not going to cover that. But as you can see, it deletes the um, in this case, the behavior that we should see. So if that's the case, it should delete this here, and we'll confirm it here in a minute. So let's go ahead and delete the pod and then the PVC. All right. Um, I'm not sure how quick the deletion aspect is, but let's just check. All right. So before we, looks like it was cleaned up. So before we actually deleted the pod, right, we did an ls, right, and the opt local path provisioner directory. Then we saw that the folder existed, right, for that persistent volume, right? And then once we deleted the pod and the PVC, it was automatically deleted on disk. So that's important to know. Okay, so the documentation kind of covers that, right? Like what we just did and what we explored. So pod shouldn't the original test pod that we deployed should be deleted, but not the pod for the local path provisioner, right? That should stay there. One thing we could do is inspect the logs um, for the pod just to see what it did, and you can see here, right? So it created the helper pod to delete the PVC, and then that's the PVC was deleted, and then the logs, and then yeah. So you can actually inspect the logs to see it deleting the persistent volume that was dynamically provisioned. In fact, you can even see when it was created as well. So creating volume, PVC, at, and then the node one, which is the one that we're currently on. Honestly, obviously, there's only just one node here, right? And it even tells you that what path it was provisioned. In this case, created. So if you had some issues with the local path provisioner, you could inspect the logs, which is nice. But if you had more than one node, um, what I don't know is if it creates a pod per node or if it's just like a central pod or in this case a deployment with several replicas. So you would have to kind of there's two ways to go about it. You could get all the logs for all the pods and check, or if you had log forwarding set up, you could look at your log forwarding system uh, that hosts all the logs and then review through there. Nice thing is you have timestamps, so that would work, help you out. So with that, I believe that's kind of like the end of what I wanted to cover today. There's a small little tidbit about Cilium and um, why I didn't cover include it. Uh, Cilium was used in the original documentation that I was referencing to, but it doesn't really make sense to use Cilium right now in a single node. Um, might have I think I do have a Cilium kind of mini walkthrough, but not in a single node cluster. Uh, might be in the two node cluster documentation that I have. But that's all I had. Well, I hope that this is helpful for those who are trying to learn, um, or increase whatever knowledge they have. Um, and if you think there's room for improvement on my part, please let me know. So Thanks for joining. I hope you guys take care. Bye.